Now, in this lecture, we'll find out the area of the green shape. In the drawing, we have a quarter circle. AOB is a quarter circle. And we have also tangent QP, that is tangent to this quarter circle here at this point. Line segment BQ equals to 3 units in its length. Line segment AP equals to 6 units. This is angle BQP, that is a right angle, and this is angle APQ, this is also equals to 90 degrees in its size. Again, our mission is to find out the area of this green shape. So, first of all, we will define the point of tendency of tangent QP with this quarter circle, this point, as point S. And we will join points O and S together by a straight line. So, what is the definition of line segment OS? Line segment OS starts from point O, that is the center of the quarter circle, and ends at point S, that is the point on the quarter circle itself. This is exactly the definition of a radius. Therefore, OS is the radius of the quarter circle. We define the radius of the quarter circle as x. And therefore, OS equals to x. In the next step, we will do a construction, that is to say, from point B, we will go perpendicular on OS. So, this angle equals to 90 degrees, and this angle equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point B and OS as M. We can implement rule 1. We have the radius OS that is drawn to point S, that is the point of tendency of tangent QP with this quarter circle. And whenever you have a radius that is drawn to the point of tendency, then tangent QP will be perpendicular to the radius SO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So actually, inside quadrilateral BMQS, inside this small quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. Okay. So inside the small quadrilateral BMQS, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral BMQS as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BMQS, side BQ must be equal to the opposite side MS. But BQ equals to 3, therefore the opposite side MS must be also equal to 3 units in its length. So I write it down. MS equals to 3 units in its length. And we also have the rule that the opposite sides of a rectangle are parallel to each other. So in rectangle BMQS, side BQ is parallel to side MS. So I write it down. In rectangle BMQS, side BQ is parallel to the opposite side, side MS. Repeat again. Rectangle BMQS, side BQ is parallel to side MS. Side BQ also equals to side MS, but side BQ is also parallel to side MS. So we know that OS is the radius of this quarter circle. So OS is a radius, it is absolutely a straight line. So OS is a straight line, and MS is part of the straight line OS that is parallel to BQ. So if part of the straight line OS is parallel to BQ, then the straight line OS itself must be also parallel to BQ. So write it down. The straight line OS itself must be also parallel to BQ. According to the rule that if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. MS is parallel to BQ, so the straight line OS must be also parallel to BQ. Okay, so I found out that in quadrilateral, in rectangle BMQS, actually we have here quadrilateral OBQS. Inside this quadrilateral OBQS, side OS is parallel to side BQ. Again, inside this quadrilateral OBQS, side OS is parallel to side BQ. And therefore, this quadrilateral OBQS is a trapezoid. Quadrilateral OBQS is a trapezoid. Repeat again, quadrilateral OBQS is a trapezoid. Actually, the definition of a trapezoid is a quadrilateral with one pair of parallel sides. And therefore this quadrilateral OBQS that has one pair of parallel sides, that is to say side OS is parallel to side BQ, is defined as a trapezoid. Okay, repeat again, this quadrilateral OBQS is a trapezoid. What is the length of line segment OM? For the drawing, it is very easy to see that OM equals to OS minus MS. Again, OS minus MS equals to OM. So I write it down. OM equals to OS minus MS. So OM equals to OS. OS is the radius of the quarter circle that is equal to X according to our definition, minus MS. MS equals to 3. So in total, OM equals to X minus 3. OM equals to X minus 3 units in its length. So I write it down in the Roman itself. Line segment OM is equals to X minus 3 units in its length. In the next step, we will do another construction, that is to say, from point A, we will do a perpendicular on OS. Again, from point A, we will do a perpendicular on OS. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as N. So actually, by doing this construction, we can do quadrilateral NASP. Inside this quadrilateral NASP, we have 1, 2, 3 right angles, and therefore the size of this fourth missing angle must be equal to 90 degrees in its size, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside the quadrilateral NASP, we have 4 right angles, therefore any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral NASP as a rectangle. So in rectangle NASP, side NS must be equal to the opposite side AP, according to the rule that the opposite sides of a rectangle are parallel to each other. So AP equals to NS, but AP equals to 6, therefore NS must be also equal to 6 units in its length. NS equals to 6 units in its length. And also, we have the rule that the opposite sides of a rectangle are parallel to each other. So in rectangle NSPA, side NS is parallel to the opposite side AP. So I write it down. In rectangle NASP, side NS is parallel to the opposite side, side AP. Repeat again. In rectangle NASP, side NS is parallel to the opposite side, side AP. So NS is parallel to AP. NS is part of the straight line OS. So part of the straight line OS is parallel to AP. Therefore, the straight line OS itself must be also parallel to AP. Okay, so the straight line OS is also parallel to AP. OS is parallel to AP, so in quadrilateral OSPA, this quadrilateral OSPA, side OS is parallel to side AP. Therefore, quadrilateral OSPA is a trapezoid. So write it down. Quadrilateral OSPA is a trapezoid. And then quadrilateral OSPA is a trapezoid because it has one pair of parallel sides. That is to say, side OS is parallel to side AP. Quadrilateral OSAP is a trapezoid. So actually, in conclusion, we found out that quadrilateral OBQS is a trapezoid and quadrilateral OSPA is also a trapezoid. It is very easy to see that this shape in total, AOBQSP, consists of those two trapezoids. Okay, so the sum of the areas of those two trapezoids will be equal to the area of this shape in total. Again, the area of this trapezoid OBQS plus the area of this trapezoid OSPA will be equal to the total area of this shape OBQSPA. Okay, so in the next step we find out the length of this line segment ON. What is the length of ON? From the domain it is very easy to see that ON equals to OS minus NS. Again, ON equals to OS minus NS. So I write it down. ON equals to OS minus NS. So ON equals to OS. OS is the radius of the concentric circle that is equal to X minus NS. We already found out that NS equals to 6. So in conclusion, we found out that the length of line segment ON is actually equals to X minus 6. So I write it down. The length of this line segment ON is equals to X minus 6 units. In the next step, we'll focus on this right triangle ONA. And we'll define the size of this angle as alpha. So in the right triangle AON, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus alpha. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So the missing angle here equals to 90 degrees minus alpha. We define 90 degrees minus alpha as beta, and therefore the missing angle here equals to beta. So if 90 degrees minus alpha equals to beta, it means that 90 degrees minus beta is equals to alpha. If you just subtract from this equation beta and add alpha, we'll get that 90 degrees minus beta equals to alpha. So in the next step, we'll focus on this. What is the size of this missing angle? actually the size of this missing angle, it will be equal to the big angle BOA or AOB is equal to 90 degrees. It is a right angle minus angle alpha. Again, 90 degrees minus alpha equals to this missing angle. So the missing angle here equals to 90 degrees minus alpha. But according to our definition, 90 degrees minus alpha equals to beta. Therefore, the missing angle here equals to beta. In the next step, we'll focus on the right triangle, triangle OBM. In the right triangle OBM, this angle equals to beta, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus beta. Again, the missing angle must be equal to 90 degrees minus beta. But we already found out that 90 degrees minus beta equals to alpha. Therefore, the missing angle equals to alpha. What is the definition of line segment OB? Line segment OB starts from point O, that is the center of the quarter circle, and ends at point B, that is a point on the quarter circle itself. This is exactly the definition of a radius. Therefore, OB is the radius of this quarter circle, is equal to x. Likewise, line segment OA starts from point O, that is the center of the quarter circle, and ends at point A, that is the point of the quarter circle itself. Therefore, OA is also the radius of this quarter circle, that is equal to x, according to our definition. In the next step, we will prove that those two right angles can go into each other. Repeat again, we will prove that this right angle, triangle ONA, is congruent to this right angle, triangle OMB. So I'll write it down. We will prove that the right triangle ONA, this right triangle, congruent to this right triangle, triangle OMB. So, why those two right triangles can go into each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle ONA. In the right triangle ONA, and it is equal to this angle, it is actually angle OMB. In the right triangle, triangle OMB. So, repeat again. Angle ONA in the right triangle ONA equals to angle OMB. In the right triangle OMB, they are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles, they are both equal to alpha, therefore they are equal to each other. So this is angle AON in the right triangle in the right triangle ONA, and it is equal to this angle. It is equal to this angle. This is actually angle OBM in the right triangle OMB. Repeat again. angle AON in the right angle ONA equals to angle OBM in the right angle OMB. They are both equal to alpha, therefore they are equal to each other. And those two angles, they are both equal to beta, therefore they are equal to each other. So this is angle OAM OAN in the right angle ONA, and it is equals to this angle, that is actually angle MOB in the right angle OMB. Repeat again, angle ONA in the right angle ONA equals to angle MOB in the right angle OMB. They are both equal to beta, therefore they are equal to each other. And finally, side OA in the right angle ONA is equal to side OB in the right angle OMB. They are both the radii of the quarter circle that is equal to x, therefore they are equal to each other. Repeat again. Finally, side OA in the right angle ONA is equal to side OB in the right angle OMB. They are both the radii of the circle that is equal to x, therefore they are equal to each other. So we actually proved that the right triangle ONA congruent, this is the sign of congruent, to the right triangle OMB according to angle side angle rule. So what is angle side angle rule? Angle side angle rule is that if you prove that two angles and the side that included between the two angles in one triangle are correspondingly equal to two angles and the side that included between the two angles in a second triangle, then you actually proved that the two triangles can go into each other according to angle side angle rule. And in here we proved that those two angles alpha and beta, and the side that included between those two angles, that is actually side OA, are correspondingly equal to those two angles that are also alpha and beta, and the side that included between those two angles, that is actually side OB in the right angle OMB. Therefore, those two right angles can go into each other according to angle side angle rule. And from the fact that those two right angles can go into each other, we will conclude that side ON in the right triangle ONA is equals to side MB in the right triangle OMB. Repeat again. Side ON in the right triangle ONA equals to side MB in the right triangle OMB according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say ON and MB, must be also equal to each other. But we have already found out that ON equals to x minus 6. Again, ON equals to x minus 6. So we can write here that ON is equals to x minus 6, and from this equation x minus 6 equals to ON equals to MB, we will derive that side MB is also equals to x minus 6. So actually this is side MB This is equal to x minus 6 units in its length, so I write it down. Side MB is equal to x minus 6 units in its length. Likewise, because of the fact that those two right triangles can go into each other, we will conclude that side OM in the right triangle OMB is equal to side NA in the right triangle AOM. And again, we conclude that side OM in the right triangle OMB equals to side NA in the right triangle ONA. According to the same rule, the corresponding angles in congruent triangles are equal to each other. But we have already found out that OM, side OM is equal to x minus 3. OM equals to x minus 3. So we can write here that OM equals to x minus 3. And from this equation, x minus 3 equals to OM equals to NA, we derive that NA is also equals to x minus 3. NA equals to x minus 3 units in its length. So we can write here that NA is equals to x minus 3 units in its length. In the next step, I will copy the right triangle ONA in the new page, and we'll implement on this right triangle ONA the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side ON equals to x minus 3. Side NA equals to, actually, side ON equals to x minus 6. Here, side ON equals to x minus 6. And side NA equals to x minus 3 units in its length. The hypotenuse OA, it is also the radius of the quarter circle, it is equal to x. So actually, this is the right triangle ONA that I copied from the original drawing. According to the Pythagoras theorem, in the right triangle ONA, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ONA is OA. Therefore, the square of the hypotenuse is OA squared, and it is equal to ON squared plus NA squared. OA equals to x, therefore OA squared is x squared, and it is equals to ON squared. ON is x minus 6, therefore ON squared is x minus 6 squared plus NA squared. NA is x minus 3, therefore NA squared is x minus 3 squared. In conclusion, found out that x squared equals to x minus 6 squared plus x minus 3 squared. Here we'll open the brackets on this side of the equation and we'll get that x squared equals to x minus 6 squared. X minus 6 squared equals to x squared plus 6 squared, that is 36, minus 2 times x times 6 is minus 12x, plus x minus 3 squared. X minus 3 squared equals to x squared plus 3 squared, that is 9, minus 2 times x times 3, that is minus 6x. So here we have x squared on both sides of the equation, so x squared will get cancelled. So on this side of the equation we're left with nothing, that is to say 0. On the other side of the equation we have 36 plus 9, that is 45. And we have also minus 12x minus 6x is minus 18x. Plus x squared. So actually we found out that x squared minus 18x plus 45 equals to 0. So this is a quadratic equation, and general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X is equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, x squared minus 18x plus 45 equals to 0, the coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to 45. Now we'll put the data inside this equation in order to find out the value of the values of x. X is the radius of the quarter circle. So according to this general formula, x equals to minus b. Minus b in our specific quadratic equation is minus 18. Therefore, b is minus 18. Therefore, minus b is minus 18. That is plus 18. Plus minus square root of b squared. B is minus 18. Therefore, b squared is minus 18 squared. That is 324. Minus 4 times a. A is 1. So minus 4 times 1 is minus 4. Times c. That is 45. So minus 4 times 45 is minus 180 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. In conclusion, found out that x equals to 18 plus minus, inside the root we have 324 minus 180 is 144 divided by 2. So x equals to 18 plus minus the square root of 144 is 12 divided by 2. So here we will have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12 over 2. 18 plus 12 is 30, and 30 over 2 is 15. According to the first solution, x equals to 15. This is the radius of this quarter circle, x equals to 15 units in its length. And we also have a second solution that is possible for x. The second solution for x is that x equals to 18 minus 12 over 6, or over 2. So 18 minus 12 is 6, and 6 over 2 is 3. So according to the second solution, x equals to 3 units in its length. But this solution is incorrect solution. Why? Because we found out actually that the length of this line segment MB equals to x minus 6. So write it down. MB equals to x minus 6 units in its length. MB is the length of this line segment, so MB is a length. As a length, it must be a positive number. That is to say, MB that is equals to x minus 6 in its length must be a positive number. That is to say, x minus 6, the length of MB, must be greater than 0. If x minus 6 is greater than 0, it means that x is greater than 6. So just add 6 to this inequality. So in the conclusion, found out that x must be greater than 6. If x must be greater than 6, it can never be equal to 3, that is less than 6. So the solution that x equals to 3 is the correct solution. We will cancel the solution, and we are left only with the third solution that is possible for x. That is to say, x equals to 15 units in its length. X equals to 15 units. So line segment OB, that is x, is equal to 15 units. Here, line segment OA, this is also x, is 15 units in its length. We have here BM is equal to x minus 6. It is also equal to QS, and QS equal, because BM QS is a rectangle and the opposite sides of a rectangle are equal to each other. So QS equals to x minus 6. X minus 6, what is the value of x minus 6? X is 15. So 15 minus 6 is 9. So QS equals to 9 units in its length. What is the length of this SP? SP and SPA is a rectangle. The opposite sides of a rectangle are equal to each other. So NA equals to SP, but NA equals to x minus 3. Therefore SP also equals to x minus 3. X minus 3 is 15 minus 3, that is 12. In conclusion, we found out that the length of line segment SP is equal to 12 units. And also OS is the radius of the quarter circle, that is equal to 15. Okay. So, in the next step, I will present to you the formula for the area of a trapezoid. I repeat again that a trapezoid is a quadrilateral with one pair of parallel lines. So here we have quadrilateral ABCD. In quadrilateral ABCD, side AD is parallel to side BC, and therefore quadrilateral ABCD is a trapezoid. So what is the area of trapezoid ABCD? The area of trapezoid ABCD first of all, the two parallel sides, side AD and side BC, are defined as the bases of the trapezoid. So AD is the first base and BC is the second base. So the area of this trapezoid ABCD, equals to the sum of its bases, that is to say, it is AD plus BC. Times the height. The height must create 90 degrees with the base. Actually, the height must create 90 degrees with those two bases, because of the fact that the two bases are parallel to each other. If the height creates 90 degrees with one base, it must create 90 degrees with the other base, because they are parallel to each other. So the sum of the bases, that is AD plus BC, times the height. Again, the height must create 90 degrees with the two bases divided by 2. So if this angle is a right angle, and this angle is also a right angle, the height is DC, because DC creates 90 degrees with AD and the second base BC. So if those two angles are right angles, then the height is DC. Repeat again, the area of any trapezoid equals to the sum of the bases times the height over 2. Again, if one of the sides of the trapezoid create 90 degrees with the two bases, then that side will be the height. In this case, CD is the height, because those two angles are both equal to 90 degrees. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the whole shape OAPSQB minus the area of this quarter circle OAB. Okay, but the whole shape BOAPSQB consists of those two trapezoids. So the sum of the areas of those two trapezoids is equals to the area of the whole shape OAPSQB. So the sum of the areas of the two trapezoids OBQS plus the area of trapezoid OSPA minus the area of this quarter circle OAB will be equal to the area of this green shape. So I write it down. The area of trapezoid OBQS plus the area of the second trapezoid OSPA. And again, the area of trapezoid OBQS plus the area of trapezoid OSPA, the sum of the areas of those two trapezoids will give us the area of this whole shape in total, and the area of the whole shape in total minus the area of quarter circle AOB will give us the area of the green shape. So minus the area of the quarter circle AOB is equals to the area of the green shape. Okay, so what is the area of trapezoid OBQS? What is the area of this trapezoid OBQS? The area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, because BQ is parallel to OS. We proved it in the beginning of the lecture. So it is BQ plus OS times the height. Again, the height must create 90 degrees with the two bases. Side QS creates 90 degrees with the first base, and it creates also 90 degrees with the second base. Therefore, side QS is the height to the base. So it is times QS, that is the height, over 2. Plus the area of trapezoid OSPA. What is the area of trapezoid OSPA? It is equals to the sum of its bases, that is actually OS plus AP, times the height. Again, the height must create 90 degrees with the two bases. Side SP creates 90 degrees with the two bases, OS and AP. Therefore, side SP is the height over 2 minus the area of the quarter circle AOB. The area of any quarter circle is equal to the area of the circle over 4. Quarter is 1 over 4. Okay. So the area, we know that the radius of the quarter circle is of course equals to the area. The radius of the quarter circle equals to the radius of the circle, that is x. Therefore, the area of the circle will be equal to pi x squared. And when we divide the area of the circle by 4, we get the area of the quarter circle. It is a quarter of a circle. Okay. That is to say, we must divide the circle by 4 in order to get the area of the quarter circle. So what is here? BQ equals to 3. OS is the radius of the quarter circle, that is equal to x, and x equals to 15. So it is 3 plus 15, that is the sum of the two bases, times QS. QS is 9, the height is 9 units, divided by 2. So here 3 plus 15 is 18. 18 over 2 is 9, and 9 times 9 is 81. In conclusion, we found out that the area of the small trapezoid OBQS, this trapezoid OBQS, is equals to 81 square units, plus the area of trapezoid OSPA. So it is plus OS is 15, plus AP is 6, times the height SP, that is 12, over 2. Okay, so here we have 15 plus 6 is 21, and 12 over 2 is 6. 21 times 6 is 126. In conclusion, found out that the area of the big trapezoid OSPA is equal to 126 square units, and the sum of the areas of those two trapezoids, that is to say 81 plus 126, it is equal to the area of this whole shape in total. We have to subtract from the area of the whole shape in total the area of this quarter circle AOB. The area of the quarter circle AOB equals to pi x squared over 4. So it is pi x is 15, therefore x squared is 15 squared, that is 225 over 4. In conclusion, found out that the area of quarter circle AOB equals to 225 pi over 4. 225 pi over 4 is equal to 176.716 square units. So the sum of the areas of the two trapezoids OBQS plus trapezoid OSPA is 81 plus 126, that is 207. That is to say, the area of this whole shape in total, it is equal to 207 square units, minus the area of the quarter circle AOB, that is equal to 176.716 square units. So 207 minus 176.716 is equal to 30.285 square units. In conclusion, found out that the area of the green shape in total is equal to 30.285 square units. And that is the answer to the question. Repeat again. The area of this green shape, equals to 30.285 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. So, in the drawing, we have a quarter circle, AOB is a quarter circle, and we also have tangent QP, that is tangent to this quarter circle here at this point. We also know that line segment BQ equals to 4 units, line segment AP equals to 6 units. This is angle PQP, that is a right angle, and this is angle APQ, that is also a right angle. Again, our mission is to find out the area of this green shape. So, in the first step, we defined the point of tendency of tangent QP with this quarter circle, this point as point S. Then we join points O and S together by straight line. Point O is the center of the quarter circle, point S is the point of the quarter circle itself, therefore OS is the radius of the quarter circle. OS is the radius of the quarter circle. We define the radius of the quarter circle as X. Therefore OS that is the radius of the quarter circle, equals to x, or s equals to x. In the next step, we join points. So OS is the radius of the quarter circle. We can implement all one. The radius OS is drawn to point S, that is the point of tendency of tangent QP with this quarter circle, and whenever you have a radius that is drawn to the point of tendency, then tangent QP will be perpendicular to the radius SO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, we did a construction. That is to say, from point B, we do perpendicular on OS. Again, from point B, we do perpendicular on OS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point B and OS as M. So inside quadrilateral, small quadrilateral BMSQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here, the missing fourth angle here must be equal to 90 degrees in its size. So inside quadrilateral BMSQ, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to this quadrilateral BMSQ as a rectangle. And you also know that the opposite sides of a rectangle are equal to each other. That is to say, side BQ equals to the opposite side MS in rectangle BMQS. But BQ equals to 3, therefore MS must be also equal to 3 units in its length. And we also have the rule that the opposite sides of a rectangle are parallel to each other. So in rectangle BMQS, side BQ is parallel to the opposite side MS. I repeat again, in rectangle BMQS, side BQ is parallel to the opposite side MS. Okay. So MS is parallel to BQ. OS is the radius of this quarter circle, therefore it is absolutely a straight line. So OS is a straight line, and part of the straight line OS, that is MS, is parallel to BQ. So if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. So because of the fact that part of the straight line OS, that is MS, is parallel to BQ, then the straight line OS itself must be also parallel to BQ. So you can write down that OS is also parallel to BQ. So inside quadrilateral OBQS, in this quadrilateral OBQS, side OS is parallel to side BQ, therefore this quadrilateral OBQS is a trapezoid. Again, quadrilateral OBQS is a trapezoid. Why? Because it has one pair of parallel sides. Okay, what is the length of this line segment OM? OM equals to OS minus MS. Again, OM equals to OS minus MS. So OM equals to OS minus MS. OM equals to OS. OS is the radius of the quarter circle is equal to X minus MS. MS equals to 3. So if we're going to find out that OM equals to X minus 3 units in itself, OM equals to X minus 3. In the next step, we did another construction, that is to say, from point A, we go perpendicular on OS. Again, from point A, we go perpendicular on OS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as M. By doing this construction, we created quadrilateral ANSP. Inside quadrilateral ANSP, we have 1, 2, 3 right angles. The fourth missing angle must be also equal to 90 degrees. So inside quadrilateral ANSP with 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral ANSP as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ANSP, side AP must be equal to the opposite side, side NS. But AP equals to 6, therefore NS must be also equal to 6 units instead. NS equals to 6 units. Likewise, we have also the rule that the opposite sides of a rectangle are parallel to each other. The opposite sides of a rectangle are parallel to each other. So here, in rectangle ANSP, side AP must be parallel to side NS. So repeat again. In rectangle NASP, side NS is parallel to the opposite side, side AP. Repeat again. In rectangle ANSP, side AP is parallel to side NS. But NS is part of the straight line OS. Again, NS is part of the straight line OS. So if part of the straight line is parallel to another straight line, then the straight line OS itself must be also parallel to AP. Therefore, OS must be also parallel to AP. OS is parallel to AP. So actually found out that in quadrilateral OSPA, inside this quadrilateral OSPA, side OS is parallel to side AP. Therefore, this quadrilateral OSPA is a trapezoid. Okay, quadrilateral OSPA is a trapezoid because it has one pair of parallel sides. And the definition of a trapezoid is a quadrilateral with one pair of parallel sides. Okay. In the next step, we found out the length of this line segment ON. ON equals to OS minus MS. Again, OS minus MS equals to ON. Here, ON equals to OS minus NS. OS is the radius of the quarter circle that is equal to X minus NS. NS equals to 6. So in total, ON equals to X minus 6. Here, I wrote down here that ON equals to X minus 6. In the next step, we found out what is the definition of line segment OB. Line segment OB starts from point O, that is the center of the quarter circle, and ends at point B, that is the point of the quarter circle itself. Therefore, OB is the radius of the quarter circle that is equal to X. Exactly for the same reason, OA is also the radius of the quarter circle that is equal to X according to our definition. In the next step, we focus on the right angle AON. In the right angle AON, we define this angle as alpha. So in the right angle AON, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. But we defined 90 degrees minus alpha is beta, therefore the missing angle here equals to beta. Then we found out the size of this missing angle. It is very easy to see that the size of this missing angle will be equal to the size of the big angle, that is actually angle AOB, that is equal to 90 degrees, minus this angle, that is alpha. So the big angle that is 90 degrees minus alpha equals to the missing angle. So this missing angle equals to 90 degrees minus alpha. But 90 degrees minus alpha equals to beta, therefore the missing angle here equals to beta. So in the right angle OMB, this angle equals to beta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus beta. But 90 degrees minus beta equals to alpha. Therefore the missing angle equals to alpha. In the next step, we proved that those two right angles can go into each other. So why those two right angles can go into each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And also, if those two angles are both equal to beta, therefore they are equal to each other. So all the triangles in the right triangle AON are correspondingly equal to all the triangles of the right triangle OBM. And finally, side AO in the right triangle AON equals to side OB in the right triangle OBM. They are both the radii of the circle that is equal to x, therefore they are equal to each other. In conclusion, found out that those two right triangles can go into each other according to angle side angle rule. So what is angle side angle rule? Angle side angle rule is that if we prove the two angles and the side that included between the two angles in one triangle are correspondingly equal to two angles and the side that included between the two angles in a second triangle, then we actually proved that the two triangles can go to each other according to angle side angle rule. And we actually proved that those two angles, that is to say alpha and beta, and the side that included between those two angles, that is side AO and the right triangle AON, are correspondingly equal to those two angles that are also alpha and beta, and the side that included between those two angles, that is side OB in the right triangle OBM. Therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that side ON in the right triangle OAN is equal to side MB. Repeat again. ON equals to MB. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding sides, that is to say ON and MB, must be also equal to each other. But we have already found out that ON equals to x minus 6. So we can write here that ON equals to x minus 6. And for this equation, x minus 6 equals to ON equals to MB, we will derive that MB also equals to x minus 6. Here, side MB equals to x minus 6. Likewise, from the fact that those two triangles can go into each other, we will derive that side OM in the right triangle OBM is equals to side AN in the right triangle AON. Repeat again, side OM equals to side AN. But we have already found out that OM equals to x minus 3. Here, OM is equals to x minus 3. So we can write here that OM equals to x minus 3, and from this equation, x minus 3 equals to OM equals to AN, we derive that AN is also equals to x minus 3. Yeah. This is side AN, this is equals to x minus 3, and it's instead. The next step, I copied the right triangle AON in a new page and implemented in this right triangle AON the Pythagoras theorem. So this is the right triangle AON that I copied from the original drawing. Here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle AON, AO square equals to ON square plus NA square. Again, AO square or OA square equals to ON square plus NA square. OA is x, therefore OA square is x square plus ON square. ON is x minus 6, therefore ON square is x minus 6 square plus AN square. AN is x minus 3, therefore AN square is x minus 3 square. In conclusion, found out that x square equals to x minus 6 square plus x minus 3 square. Here we open the brackets on this side of the equation and found out that x square equals to x minus 6 square, x minus 6 square equals to x square, plus 6 squared, that is 36, minus 2 times x times 6, that is minus 12x, plus x minus 3 square. X minus 3 square equals to x square, plus 3 squared, that is 9, minus 2 times x times 3, that is minus 6x. Here we have x square on both sides of the equation, so x square will get cancelled. In this side of the equation we left with nothing, that is to say 0. In the other side of the equation we have 36 plus 9 is 45, and we also have minus 12x minus 6x, that is minus 18x, plus x square. We found out that x square minus 18 square plus 45 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say x squared minus 18x plus 45 equals to 0, the coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to 45. Okay, here. Then we put the data inside this general formula in order to find out the value of the values of x. According to this general formula, x equals to minus b. In our specific quadratic equation, b is minus 18, therefore minus b is minus 18, that is plus 18, plus minus square root of b squared. b is minus 18, therefore b squared is minus 18 squared, that is 325, minus 4 times a is 1, so minus 4 times 1 is minus 4, times c, that is 45, minus 4 times 45 is minus 180, divided by 2a, a is 1, so 2 times a, that is 2 times 1, that is 2. So x equals to 18 plus minus 4 to 324 minus 180. So x 324 minus 180 is 144. So x equals to 18 plus minus square root of 144 over 2. The square root of 144 is 12. So in conclusion, we found out that x equals to 18 plus minus 12 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12, that is 30 over 2. 30 over 2 is 15. So according to the first solution, x equals to 15, and we also have a second solution that is possible for x. X could be also equal to 18 minus 12, that is 6, and 6 over 2 is 3. So according to the second solution, x equals to 3. But this solution is incorrect solution. X can never be equal to 3. Why x can never be equal to 3? Because of the fact that we already found out that 97bm equals to x minus 6 units in its length. 97mb equals to x minus 6 units in its length. So mb is a length, and as a length it must be a positive number. So the length of mb is minus 6, that must be a positive number. If x minus 6 is a positive number, it means that it's greater than 0. If x minus 6 is greater than 0, it means that x must be greater than 6. If x must be greater than 6, it can never be equal to 3, that is less than 6. So this solution is a correct solution, and we left only with the second solution that is possible for x. This is to say x equals to 15 units in its length. Here, OB, this is x is 15, OA, that is x is 15, OS, that is x is 15, QS is x minus 6, that is 15 minus 6, that is 9, SP is x minus 3, that is 15 minus 3, that is 12. So in the next step, I presented to you the general formula for the area of any trapezoid. Again, trapezoid is a quadrilateral with one pair of parallel sides. Trapezoid quadrilateral ABCD is a trapezoid. Why? Because of the fact that side AD is parallel to side BC. We defined, actually, the two parallel sides are defined as the bases of the trapezoid. So AD is the base, and BC is the second base. So the area of any trapezoid equals to the sum of its bases, that is to say AD plus BC, times the height. The height must create 90 degrees with the two other bases. If CD creates 90 degrees with two other bases, then CD is the height. But if CD doesn't create 90 degrees with the two other bases, we just draw perpendicular the two other bases, and the perpendicular will be the height. So it is times, so the area of any trapezoid equals to the sum of its bases, that is AD plus BC, times the height over 2. So what is the area of this green shape? The area of the green shape, it is very easy to see from the drawing, that the area of this green shape equals to the area of this shape in total. This is to say the whole shape, that is AOBQSP, minus the area of this quarter circle AOB. But the whole shape consists of those two trapezoids. Therefore, the sum of the areas of those two trapezoids will be equal to the area of this whole shape in total. Therefore, the area of the whole shape in total equals to the area of trapezoid OBQS plus the area of trapezoid OSPA. Repeat again, the area of the whole shape, the area of the green shape equals to the area of the whole shape in total. The area of the whole shape in total equals to the area of trapezoid OBQS plus the area of trapezoid OSPA. Why? Because the whole shape in total consists of those two trapezoids. Okay? So the area of the whole shape in total minus the area of this quarter circle AOB equals to the area of the green shape. Okay? Minus the area of the quarter circle AOB. What is the area of trapezoid OBQS? The area of trapezoid OBQS equals to the sum of the two bases, that is BQ plus OS, BQ plus OS times the height QS. Why the height is QS? Because it creates 90 degrees with the two other bases. So it is times QS over 2. Okay, BQ is 3, OS is 15, QS is 9 divided by 2. 3 plus 15 is 18, 18 over 2 is 9, and 9 times 9 is 81. Because we found out that the area of this trapezoid OBQS is equal to 81 square units, plus the area of this trapezoid OSPA. What is the area of this trapezoid OSPA? It equals to the sum of its bases, that is OS plus AP, OS plus AP times the height SP. Why SP is the height? Because it creates 90 degrees with the two other bases. So the height is SP over 2. OS is 15, AP is 6, SP is 12 over 2. 15 plus 6 is 21 times 12 over 2 is 6. 21 times 6 is 126. So we found out the area of this trapezoid OSPA, it is equal to 126 square units. It is equal to 126 square units. Minus the area of this quarter circle AOB. The area of any quarter circle equals to the area of the circle over 4. The radius of the circle is x, therefore the area of the circle is pi x squared. Pi x squared over 4 is the area of the quarter circle AOB. X is 15, x squared, therefore x squared is 15 squared, that is 225. So in total, the area of the quarter circle AOB equals to 225 pi over 4. 225 pi over 4 is equal to 176.716 square units. So the area of the whole shape in total equals to the sum of the areas of the two trapezoids. This is actually 81 plus 126, that is 207. That is to say, the area of this whole shape in total, it is equal to 207 square units. So the area of the whole shape in total minus the area of this quarter circle AOB is equal to the area of the green shape. And the area of the quarter circle AOB equals to 176 on 716. So the area of the whole shape in total, that is 207 square units, minus the area of the quarter circle, that is 176.716 square units, equals to the area of the green shape. So 207 minus 176.716 equals to 30.285 square units. So if we found out the area of this green shape equals to 30.285 square units. Okay, thank you very much.